Everyone, shall we start with this session? The next session is going to be about grammars and parsing, and we start with a paper about a reference GLL implementation and by Adrian Johnstone from Royal Holloway, University of London. The floor is yours.
Thank you very much. Nice to see old friends and collaborators in the audience. I'll start with some acknowledgements from our funders, and also I thought I'd put this picture up because actually Ilko took it a few years ago. It's a picture I like, and it gives me an opportunity to acknowledge my not co-author on this occasion, but usually co-author Elizabeth Scott, who's hiding back there somewhere. She's the program chair for this conference, which is why this is a singleton paper. This is an updated version of a slide that I show whenever I do one of these talks, and it's broadly speaking the history of generalized parsers as they're being used out there. And I'll elucidate. There's a lot of information on this slide, and of course I'm not expecting you to take it all in. The green bits up there are all GLL related, so that's really the topic of today's conversation. And there are some other generalized parsers. You might call this the Amsterdam branch here, and the London branch of GLR, and there are some other things here, Nigel, horseman stuff.
Adrian.
Let me just summarize by saying this.
Can I just stop you? Can you speak into the mic?
Yeah. Is that working? Yeah. I can't hear any better. Okay, right. So, is that actually switched on? There we go. Now I can hear it. This is why I wasn't using the mic, because I couldn't hear you. This is the summary. This is all you've got to take away from this slide. The stuff down at the bottom here, the near-deterministic textbook orthodoxy, that's what every undergraduate is taught. You know, bit of LL parsing, bit of LR parsing, and they can just about pass an exam question, write the automata. And, you know, that's essentially parsing for most people. It all kind of stopped in the mid-70s. If you go and look in the reverse engineering world and in various other worlds, the semantics world, you'll find generalized parsers appearing. And that central branch there represents work mostly out of CWI Amsterdam. There's Ilko there, for instance, in '97. Now, our particular branch of GLR ends up with this binary right null GLR parsing there, Acta Informatica 07, and that's the target for most of our work in generalized parsing, and we believe that's our fastest algorithm. However, I'm not aware of any implementations out there of BRN-GLR because, to be honest, it's quite dense and quite hard. Well, obviously, I have implemented it, but I'm not aware that anybody else has had a go at it, even though we think it's probably the fastest thing that you're going to find. So instead, we have generalizations of LL parsing, the stuff that's in green up there, and the paying proposition for GLL is that it's simple to understand. Now then, that leads us to a problem. The real purpose of this paper is to sort my inbox out, because we think GLL is really simple, but sometimes it seems most weeks we get a paper, we get an email from folks saying, well, we don't really understand what's going on. Can you tell me what's wrong with my implementation? Ooh, that's a really hard one, because the answer, of course, is no. Debugging someone else's implementation is a very intensive activity. Even worse, we quite often get emails from people saying, well, we implemented all of GLL and we chopped this bit out and it doesn't seem to have broken, so we don't think it's necessary. And that's really troubling, of course, because if somebody takes one of your algorithms and cuts a bit out, then they probably haven't understood what it was there for in the first place. This all came to a bit of a head in Athens, actually, at ETAPS in 2019, when somebody sat down for lunch with us and said, have you seen that Sonar Source blog post on GLL? And we hadn't. Had a look, it was nice. And in the middle of it, it said, it's great, but there isn't even a reference implementation. And I thought, I better do something about that. And that's what this paper is. Okay, now let's just go through the rest of the world. Okay, so, you know, let's get back to the textbook orthodoxy. The emphasis there is on deterministic parsing, linear parsing, and here's something that goes very, very fast in a straight line, and is my metaphor for, you know, your typical LALR parser. It's terrific if what you want to do is handle something near deterministic, but it's going to flip over if you drive it too hard. There are a welter of alternative technologies out there now, by which I include things like pegs and extensions of various kinds to near deterministic algorithms, which are also fantastic, but are characterized by only returning a single derivation. And my metaphor for that is Formula One car, which is very fast, but it needs to go on a special surface, and it's always going to take one route. And if there's another way across the track, it's not going to take it. In fact, it's not even going to tell you that those other routes exist. What we need for many of our applications, in particular for semantics and the kind of thing that Judy was talking about this morning, we need things that are like this. Now, Land Rovers are slow and heavy and rather resource intensive, but they will go everywhere. And just to sort of really emphasize that, while this video is running, I'll give you some more justification. When I was writing this paper, I had a little poke around, and I found, actually somewhat to my surprise, that GCC, no less, stopped using generated parsers in about 2004, so nearly 20 years ago. And the front-end parser, according to what I read, I'm not a GCC developer, the front-end parser for GCC has been handcrafted for nearly 20 years. Now, we must view this as a retrograde step, because we're interested in systems which can be formally specified and analyzed, and a bunch of code purporting to be the front end for one of the most commonly used compilers. For it not to be in that category is quite alarming. And of course, what we would like to do is to put a proper generalized parser with a principled disambiguation in there instead. It's a good job the sound was switched off, by the way, because at the end of that little video clip, when that Range Rover finally gets over that extraordinary cliff, there is some swearing. Now, leaving aside utility and being able to reason about the correctness of these very important tools that underpin so much of our software infrastructure, there's also the other aspect of the science, which is not correctness, but which is performance. Now, the three graphs here that are in this sort of magenta color were generated for Splash in 2013 when we were in Indianapolis. It was the parsing at Splash mini workshop. And what I did there was I took what we call our torture test, which is this uncomfortable looking grammar up the top here, the one that says we're going to match a string of Bs, but we're going to do it in a particularly stupid fashion by introducing a heap of ambiguity. And we use this grammar a lot because it triggers the cubic worst case bound for most of the algorithms that we're interested in, and it's a one-liner. So if you've got a generalized parser, it's fun to throw this at it and see what happens. Now, those curves are all the same, almost, right up until you start looking at the axis labels. The x-axis is the length of the string. The y-axis is the number of seconds that are required to perform the parse for that length of string. And as you can see, the two at the bottom, one of them from 10 years ago, one of them from last night, the one in blue I ran last night, they're coming in under a second, but you can spend a lot more time trying to do these parsers if you want. Now, caveat, strong caveat, these are 10-year-old experiments. I have no reason to believe that those tools or any other are as slow as they were then. But the important thing is that 10 years ago, all three of these implementations were being used, so they were actually out there in the wild, they weren't just lab experiments, and yet they've got such wildly varying performance characteristics. And this is the other aspect of my inbox. It's not just, can you fix my implementation, or do you know why I get away with not doing this, but there's also the performance issue. And we've had some fairly notable software engineering outfits write to us and say, well, we built this thing, and look, it runs this fast. And then I send them something like that back, or some equivalent set of metrics, and it's a lot faster. And we often don't hear from them again. So we don't want that. We want take-up of this algorithm. So we also want to explain how we achieve some of the figures that we achieve, or at least build up to it properly. Now, there is a problem with the original presentations of GLL, and that is that really what's in the papers is a parser generator, not a parser per se. And the parser generator aspect of it puts another meta level in the explanation. And also that meta level is really kind of at machine level. There's go-tos in there, things that really are just anathema to a modern software engineer. And that does cause a lot of grief. So really what I've attempted to do is to strip GLL back to its absolute minimum, deliberately make it as stupid as possible, take out several of the optimisations that we built into the original presentation, to be honest, without even really thinking. We just chucked them in because it seemed stupid not to. So what we've got is the stupidest thing that really corresponds to GLL. And then the idea is that in a series of presentations, which begin with this paper and some extension stuff, which is already in the GitHub site, we'll begin to build it back up to something which is production level for what we're doing. And what I mean by that, if I just zoom back to the third slide, is all that stuff that's in green in the top three boxes there, and everything from full parser downwards as well. So there's a lot of variant papers out there, and that's another source of traffic in my inbox, because sometimes people pick up one of these papers and they haven't got the earlier ones, and they get a little bit confused. Now, obviously, I'm not going to go through the paper in this presentation because that will just send everybody to sleep, especially in the after lunch slot, but I will give you the overview of what is in the paper, which of course you can read. I'm not quite sure where the proceedings are. I guess they're online somewhere. It's a long time since I've seen a paper proceedings. This is the outline of the paper for this meeting. There's some discussion, the standard discussion about notation to describe context-free grammars, and a slightly careful explanation of what I mean by a compiled parser and an interpreted parser. And essentially, compiled parsers are what come out of our traditional presentation of GLL, a set of templates that are fitted together into a piece of code which you then compile and run standalone. Well, that's the alternative way of thinking about things is to say, well, I'll have a data structure in memory which represents a grammar, and I'll have a fixed piece of code which traverses that grammar and then performs the actions. I guess in some contexts we call that a table-driven parser. That's the way YAC works. It's got a tabular representation of the underlying state machine in memory, and the actual parser itself is a fixed piece of code which doesn't change from one grammar to the next and just traverses that table. So we're going to be focusing on interpreted parsers because I believe they're easier to understand, and it's very easy to derive the compiled parser from an interpreted parser when you have it. So the rest of the front material looks at our grammar representation, which I'll outline to you in a moment. It's very straightforward and talks about just how much context a context-free parser actually needs. There are three algorithms that are presented in the paper. I start off with a backtracking recursive descent parser, which has got no smarts in it at all. You know, we've all used parsers, and nearly everybody has written a parser, and the classic parser that all of our undergraduates write is a recursive descent parser with first and follow sets in it. Well, we could go one step back from that. You could do away with the first and follow set computations and simply have a straightforward backtracking mechanism. And that's what I do with my undergraduates. I show them that as the simplest thing I can think of, which is a parser that does something useful. What I do in the paper here, though, is I start from the traditional compiled presentation and move in a couple of steps to what I'll call a state-based interpretation, which has essentially exactly the same shape as the interpreted GLL presentation that I then give in this algorithm baseline, GLL-BL, which I'll show you in a moment. So GLL-BL, like all GLL algorithms, maintains 6 sets. And when it's running, it's essentially building these sets. They only ever get bigger. You never remove anything from the sets to first approximation. We'll get to that in a moment. And these sets, between them, dominate the performance of the algorithm because these set updates and set lookups are essentially most of the computation that's performed inside GLL. Therefore, the performance is absolutely critically controlled by the efficiency of your set representations. Now, the two variants of the algorithm that are presented in this paper are called GLL baseline and GLL hash pool. So GLL baseline uses the standard Java APIs, and the intention there is that it'll look very familiar to any conventional Java programmer. They're not going to get freaked out by it, and they should be able to read the code and see exactly what it's doing, and very quickly come to the conclusion that actually it's not doing very much. The problem with that is that the Java API, well, you need to understand that on a reasonable parse, these parsers can easily generate millions of little objects. And the object allocation overhead in Java, as in all OO languages, is non-zero. And so the GLL-HP version, the hash pool version, basically uses handcrafted memory management in a sort of very low-level C style to improve the performance, and it makes a huge difference. Okay, let's just give you a very brief overview of how this algorithm works. The idea is you take your grammar, and there's a very simple grammar with two non-terminals in it, and you split it up into fragments which roughly correspond to the basic blocks of a traditional recursive descent parser. So for instance, you'll see in orange there terminals, and where you've got a run of terminals, that's going to be a single fragment. Where you've got a non-terminal, that's going to be a single fragment. And in this presentation, there's a special fragment called end that is shoved onto the end of each alternate, and there's a left-hand side fragment which is shoved onto the front. How does that play out in code? Well, there's the same grammar and the same pictorial representation at the top, and underneath it, you can see a rendering of the data structure that is used by these algorithms. The reason why it's important to show this is because these are interpreted algorithms, and what they're going to do is they're going to traverse those data structures during the parse, and so we need to be very clear about how they're built. In the classical presentation, we use a higher level of abstraction and quite a lot of mathematical notation, which is a little bit tricky for some programmers. And we talk about the concept of a slot, which roughly corresponds to the dot, the Knuth-style item in an LR parser. Here, the slots are absolutely explicit, and we call these things G nodes, grammar nodes. And you can, I think, quite quickly see what's going on there. Each G node has got a unique number. It has a type, which is something like T or N or alt, and is actually an element of this enumeration down here. And each of these G nodes, here's the declaration, has then that unique instance number. It has a type, which is an element of that enumeration, and it just has two references, alternate and sequence, alt and sec. And the alternate, in the visualization here, the alt pointers are represented by horizontal arrows, and the sec pointers by vertical arrows. And then there's a special case of the end nodes. With the end nodes, the alt pointer points to the enclosing bracket, and the sec pointer points to the head of this sequence. You can see 23 and 24 there in that first production of X. It's very straightforward. It generalizes trivially to EBNF. As soon as you've got bracketed constructs like these red ones down here, so do first, parentheses, optional, that's the question mark that you'll see in the external syntax, positive closure, clean enclosure. Those brackets then become the thing that the alt pointer points back to. It's trivial. It's meant to be trivial. If you're looking at this thinking, God, this is pretty straightforward, Adrian, then I win, because that's exactly what I want you to think. Now, we talked about these 6 sets, and the sets work as follows. Essentially, GLL is a sequentialization of a piece of parallel processing, and we have thread descriptors which contain the context, and that's what class descriptor does. We need a graph-structured stack in the traditional manner for generalized parsers, and that has nodes and edges, and they're declared, as you can see there. The pop set, as it's presented in our classical papers, is distributed over the GSS nodes. In classical GLL, we had a single pop set with a set of pairs, and then the derivations are handled with shared packed parse forest and packed nodes. All the details are in the paper. Now, this is the filling in the chocolate. That is GLL written for Java programmers. And what I hope you can see is that the routine initializes, and then there is a labeled while loop called next descriptor, which attempts to dequeue a descriptor, and that's activating a processing thread. And then it runs around in a little loop. It switches on the kind, that's the type of the descriptor element that's coming out. And if it is a built-in or a terminal or a character, then it checks to see whether the input element matches. If it does, it updates the derivation, du of 1 there, and then it increments the input pointer and off it goes. If it doesn't match, we abort this thread of control And we do that simply by doing a continue on the next descriptor. So this thread of control is just killed dead, and we flip back up to the top of the loop. Non-terminals are trivial. We have a routine called call, which is analogous to a recursive descent call in a traditional RD compiler. And then when we come back from it, we continue with the next descriptor. If there's an epsilon, it's rather similar to a terminal, except we don't bump the pointer. And if there's a return, which is what happens at the end, then we do some processing in ret and then again continue with the next descriptor. So this is the outer control loop, if you like, for GLL. This particular version that's on the screen at the moment is extended over the paper version in that I've added the necessary cases to do parentheses and subrules, alternates within parentheses, and that's what it looks like. So we call that parenthesized BNF. I'm not going to go through all of this, but those are the bodies of the call and return function. The thing that I really want to flag up to you is the stuff in yellow is the stuff that everybody cuts out because they don't understand what it does. These are the so-called contingent pops. What's going on here is that when a non-terminal returns, when you return from a non-terminal, you need to remember that you've done that because you may do another return in a later context. And at that point, you're going to have to reactivate the return points from the earlier context. And this is by far the most subtle part of the algorithm. I would go so far as to say it's the only subtle part of the algorithm. And this is where people trip up. Okay, moving along quite quickly. Let's talk about memory management. So the problem with all those little nodes and set elements is there's millions of them, and it kills the Java allocator. A Java allocator does far more work than it needs to because it wants to do garbage collection. But these sets only ever expand to first approximation. And as a result, we can sidestep all of that, and we can allocate great big lumps of memory, and then simply say, well, okay, I need space for 6 elements now, so I'm just going to go and grab it by incrementing the pointer. And if the pointer falls off the end of a block, I'll just allocate another one. And that way, we can reduce the number of calls to the allocator by whatever figure we choose, a couple of million in this case. And it's transformational as far as the performance is concerned. And I think the lack of this kind of optimization is the thing that trips people up in terms of speed. Okay. There are a lot of variants, which I won't go through here because we're short of time, but these are all published variants of GLL which need to be fully characterized and are not in this paper because it's a 12-page conference paper. But the good news is there's a big technical report on the GitHub site which starts with this paper and is building up and will continue to build up to handle each of these, including our most recent publication, which is the multi-GLL, multi-parser, which came out in top class a month or two ago. Frankly, they made such a mess of the typesetting that we're still arguing with them about it, but it is on the website and you can read it now. And it's very important if you're interested in lexical ambiguity. This is my last slide. Is any of this worth having? Well, I've got this kind of rule of thumb that I call GEG, good enough for GNU. I've got this kind of notion that let's assume that the parsing front end for GNU executes in 0 time. If you replace that with one of our parsers, what would feel like an unbearable slowdown? And the rule of thumb that I'm using is that if you dropped a generalized parser in and it only slowed things down by 10%, people might live with it. I hope so anyway. So this is one example. Now, it's a very large example, but that's deliberately so because GLL runs cubic, worst case, and I want to show that this is valid even over very large lumps of source code. So nearly 120 kilobytes of source code there. It takes 18.8 seconds to go through GNU if you've got full optimization on. The current GLL HP, this very brain-damaged algorithm that is in this paper that doesn't have any of the optimizations in it, will rip through that in 1.35 seconds if you use the ANSI C grammar. If you use the ANSI C++ grammar, it jumps up to 7.02 seconds, which immediately tells you quite a lot about the amount of ambiguity in C++ versus ANSI C. And as we know, ANSI C, of course, is not ambiguity-free either. So we're kind of getting there. I agree that 7.02 seconds is greater than 10% of 18.8. You know, I can remember enough arithmetic to do that. But there are a whole bunch of extensions, variants, and optimisations to apply. And our goal is to get that figure for these interpreted parsers down to a couple of seconds. And at that point, we would claim that even our interpreted parser is actually something that's viable for these, this kind of production work, never mind the kind of work on semantics and checking that we heard about in the keynote this morning. Okay, I think that's it. Oh, there is one last slide. Here are some GitHub repos that you should go and have a look at if you're interested in this stuff. All of the code associated with the paper is in the top repo. It is going to carry on being developed, and I guess I ought to put a tag in there to represent today's effort. We also did some work for Toplas with very large corpora for Java 18 and standard ML, and the grammars and all of the test strings, thousands of them, are in that GitHub repo, and we intend to expand that with some corpora for other mainstream languages soon. And then if you want to go and find the primary sources for all of those things in green that were on the third slide, they're here. There's a few research directions here. Given that what we've got is a threaded implementation, it's worth asking what would happen if we actually tried running it under Java threads. We did a quick experiment a few years ago and the results were discouraging, but maybe things are better now, and anyway, we've all got graphics processors which can do interesting things too. Okay, I think I've run out of time, haven't I? I better shut up. Thank you very much for your attention.
I think
there's 3 minutes for questions.
Questions? Can you please walk up to the microphone so that people watching the stream?
I have to warn you, I'm a bit deaf, so you might have to repeat. But anyway,
a quick question, because you mentioned, I think it's a very nice approach that you use some sort of like hash pool to optimize these generalized parsing for context-free grammars, but do you also consider that this idea can apply to like layout-sensitive or indentation-sensitive languages, like Python, Haskell, YAML, whatever, they have indentations and also alignment, whatever, this kind of features?
I'm not sure I heard the question properly. Were you asking me about other languages other than the ones we've been looking at?
Yeah, like
right, okay, you're talking about the offside rule and so on. Yeah, that's not something we're addressing at this stage. I know that plenty of people have had a look at that, but we haven't gone down that road. To be honest, when I'm processing an offside rule language, I run a little preprocessor over it and stick a token in for each indentation value. I realize that that's horrifying to people that love those kinds of languages, but we've been messing with that stuff since Occam. You know, it's not just Python. These ideas have been around for a long time. So we just take a quick fix on it. That's all I have to say at the moment. But thanks for the question.
Thanks.
Any other question? Anyone?
If there's the same part of the algorithm that people are consistently screwing up and forgetting because they don't think they need it, is there an example grammar where that like obviously shows up and you just get very obvious wrong parse if you don't have that in?
Again, I didn't quite catch all of that.
The bit earlier, the part that people keep on leaving out with the
the predicted pops.
Yeah. Is there a reference grammar that if your parser will completely screw up if you don't have the
Very
the
good
code
question.
in there?
It is surprisingly hard to generate an example which will definitely kick that off. Not least of all because it totally depends on the execution ordering, and that tends to depend on the ordering in which things are coming out of these sets, and that of course depends on the hash function that you're using. So what I can say is that if you run the stuff that's in the repo with even some of the small examples, it will report how many contingent pops, as we call them, are occurring. So there are examples you can hone in on. Now, Elizabeth's on her feet, so with a bit of luck, she's got something more useful to say.
We've got an example where you can't avoid, there's no way you can process order to stop the need for contingent pops. It's in one of the papers quite early on when Ali did his thesis.
Okay, I had forgotten that. But you're right, we ought to stick that in as a standard test because, you know, that's the sort of first correctness test. But it is subtle. It's not, I mean, you know, we've got burned this way ourselves. And the other thing I would say is that the eBNF parser, it's very easy to write an eBNF recognizer, very easy, it's trivial. But to get the SPPF right, for the eBNF case is very non-trivial. We've published a version, but if I'm honest, there's a big sort of here be dragons sign over it. That's correct, but some of the later variants, which work differently, we haven't done the work to think about what the eBNF SPPF would look like in that case. And I'm not sure that we're in a hurry to do so, because it was a stressful time getting that right. Okay, thank you very much.
I think that's it with time. Yeah, let's thank the speaker again.